Hello, my name is Steven Jani, and I'm delighted to introduce you to our work on the unsupervised discovery of counterfactual physics in pixel space. This is joint work with Fabien Baradel, Natalia Nevarova, Madiane Adri, Greg Maury, and Christian Wolf. Before getting to the heart of the matter, I would like to start with a toy example illustrating the principle of counterfactual reasoning. This one is taken from an excellent presentation by Bernard Scholkoff. Imagine having access to a set of temperature measurements taken by various weather measurement stations located in the north of France. Your agent must learn the relationship between the measured average temperature and the station altitude. The classical approach consists in solving an inductive problem that is answering to how is the altitude related to the average temperature. This problem can roughly be solved by performing a linear regression. Although this leads to a result rather close to the data, this model has an important flaw. This does not tell us about the causal relationship between temperature and altitude. For the inductive agent, artificially increasing the temperature around the station will cause its altitude to decrease, which physically makes no sense. The counterfactual approach suggests changing the question. We now wonder how the measurement will evolve if the temperature or altitude were artificially changed. The question seems identical to that of inductive reasoning, yet, to answer this question, one must not only identify the linear relationship between the two quantities, but also learn the direction of the causal relationship. This is due to the what if in the formulation. This is particularly relevant in physics, where causation is considered as a fundamental axiom. In the context of machine learning, correctly capturing or modeling causal relationships can also lead to more robust prediction, in particular better generalization to out-of-distribution samples, indicating that a model has overcome the exploitation of biases and shortcuts. With filtered CoPhy, we try to propose a new approach in this direction. In this paper, we introduce both a new benchmark for unsupervised learning of counterfactual physics and also a new deep model based on the discovery of 2D key points predictors. Let's start by studying the benchmark. The filtered CoPhy benchmark is based on CoPhy, a counterfactual physics dataset introduced in a 2020 ICLR paper. Our new benchmark focuses on prediction in pixel space, as opposed to predicting object states. We also made efforts to improve the definition and increase feasibility of the task. Let's first start by looking at the structure of a single data sample. One experiment consists of two videos. The first one corresponds to the observed trajectory. Let A be the initial condition, that is, the initial position of the object on the scene. Each object has its own physical characteristics, such as mass or initial speed, which are called confounders. These characteristics are unavailable during neither training nor testing, and cannot be inferred by simple observation of a single image. The result of this trajectory is called B. In what follows, we will refer to AB as the observed trajectory of an experiment. The second trajectory results from the modification of the initial condition of the first. To obtain the new position of the object, which are noted by the letter C, a do operation is applied to A, which corresponds to a visual modification of the structure of the scene, such as moving or deleting one of the objects. In the same way, we denote by the letter D the resulting outcome, and by CD the entire counterfactual trajectory. The task to be solved in filtered CoPhy is the following. Given the observation of a single trajectory AB, can we predict the counterfactual outcome D, knowing the do operation which transforms A into C? This prediction task has been studied by Judah Pearl, who proposed a three-step solution. The abduction step consists in inferring the value of the confounders using the observed trajectory AB. We then update the causal graph using the do operation, allowing the model to be adapted to the new initial conditions. And finally, we perform the prediction of the counterfactual trajectory using the updated model. Our benchmark offers three different tasks of increasing difficulty. Ball CF is a 2D collision problem between multiple balls. Collision CF involves 3D collisions between two objects of different shapes. The most difficult task in the benchmark is certainly block tower. The cube in the scene involve highly nonlinear collisions and both brief and intense action. However, the generation of counterfactual data requires special care to ensure feasibility properties. Let's take an example in which we exceptionally color the cube according to their masses. As you can see, both towers give exactly the same results, although the confounders are different. Let us now look at the trajectory of the counterfactual outcome. Here, the do operation consisted in moving the upper cube to the left. This time, the trajectories are very different. In this situation, it is not possible to decide on the configuration of the masses from the observation of AB, and it therefore becomes impossible to predict CD. In filtered CoPhy, We took care to ensure that each experiment was feasible by simulating the trajectory of the same couple of initial conditions A and C for all possible confounders configuration. In this example, we notice that two configurations give the same result for the observed trajectory AB, but very different results for the counterfactual trajectory CD. In this case, the experiment is rejected and removed from the dataset. Maximizing this constraint could lead to trivial solutions in which the counterfactual trajectory does not depend on the confounders. We have therefore added a second constraint, which is related to the difficulty of the problem. We eliminated non-counterfactual experiments where the confounders are not needed for reasoning. We have also made several additional improvements over CoPhy, including an increase in sample rate and the use of sanity checks. You will find all the details in the appendix of the paper. Let's now look at the new model we propose to address this challenging benchmark. Since the prediction is performed entirely in the image space, a possible approach to this problem is to use an encoder-decoder structure, then performing the prediction in the generated latent space. This raises the question of the design of this latent space, especially in our situation, where the only available supervision signals are images. The ideal solution will be to train an encoder to separate the purely visual part of the video from the dynamic part. By computing an object-wise representation, the counterfactual reasoning module could focus on the physics of the problem. But for now, let's assume that we have access to such a disentangled representation and focus on the physical reasoning module. The abduction phase is performed by a recurrent graph network. To be precise, we apply the shared graph neural network to each object-centric representation forward in time and aggregate the temporal resulting representation with a gated recurrent unit. This step produces a latent and unsupervised vector that models the confounders. The actual prediction phase relies on these latent confounders to predict D from the initial object-centric representation of C. The dynamics of the scene forward in time is computed iteratively using a second graph network that operates in a higher dimensional space, where the dynamic is easier to learn. The epsilon and delta function take care of the mapping from the object-centric representation to the higher dimensional space. Now that the counterfactual dynamic model is defined, we still must find the best representation of the filtered CoPhy video to solve the task. Our encoder-decoder structure is inspired by the transporter network by Kulkarni and co-authors. This model proposes to identify a set of 2D key points and a vector of features in two images, a source and a target. Using a transport equation, the model produces new features which are then used by the decoder to reconstruct the target image. However, this model poses several problems for our application. First, it is not suitable for prediction in image space, since the reconstruction of the target requires both the key points but also the feature of the target, which should therefore also be predicted by the dynamic module. Our experiments have also indicated dynamic information leaks in the features that should only carry pure visual information. More details are available in the appendix of the paper. The major drawback here is the problem of temporal consistency of the key points. In this video, we have represented the position of the center of mass of the cube in white and the key point discovered and predicted by the transporter in black. You can see how the same key point does not track a fixed position relative to each object. Physical reasoning will be difficult on such a representation. In order to fix these issues and build our derendering module, we choose to remove the transport equation as well as the feature dependency of the target image. To compensate for the loss of information, we propose to increase the representation defined by the 2D key point with a low number of coefficients, which will be discovered in an unsupervised way by the model. We will see that a representation emerges where this coefficient represents shape information. Let's take a closer look at the structure of our derendering module. The encoder extracts a dense vector of visual feature from the source image, which will be directly used by the decoder to reconstruct the target image. A set of 2D key points is also computed on the target image, as well as shape coefficients for each key point. This representation will be used during the prediction phase. For the reconstruction of the target, the key points are encoded in the form of Gaussian mapping, and the coefficients are used to calculate a distortion filter applied to each Gaussian mapping, making them anisotropic. The resulting vector then finally passes through a CNN to reconstruct the target image. The key idea behind this deformation filter is to allow the CNN of the decoder to learn distortion from multiple oriented ellipses to target shapes. With this structure, the network naturally discovers to encode the shape of the object in the coefficient without supplementary supervision. This trick makes it possible to represent high-level geometric information in a very sparse and interpretable vector. We here see an animation illustrating walls in the coefficient space, corroborating our intuition that coefficients are related to shape. This key design choice also provides a solution to most of our problems. The use of coefficient allows us to limit the number of key points to the number of objects in the scene, which solves the problem of temporal consistency. Shape coefficients also provide a sparse representation for the prediction phase, which we discussed earlier. Training the entire pipeline directly from the video is not easy because of the low intensity of the supervision signal. Therefore, we propose to divide the training into two stages. First, the derendering module is trained to reconstruct the image without involving the dynamic module. And then, the weight of the encoder and the decoder are frozen, and the dynamic module is trained to predict the object-centric representations computed from D. During the test phase, the information coming from D is completely disconnected from the model, and the decoder uses the key point predicted by the dynamic module to reconstruct an estimate of the counterfactual video. We here show comparisons of our model with three baselines, each implementing a different level of inductive bias. PredRNN is a generic video prediction method. Quantitatively, this solution seems to give excellent results. Nevertheless, it turns out that the reconstruction quality is largely dominated by the precision with which the background is reconstructed. The actual tower is not well predicted nor reconstructed. We notice that the model struggles to keep the structural coherence of the cubes. PhiDNet is also a video prediction model targeting physical phenomena. Like PredRNN, the model fails to maintain the structural identity of the object. This is one of the strengths of representation by key points. The notion of objects is naturally embedded in the form of the data. VCDN is certainly the closest baseline to our work. It uses a transporter for the representation of key points and graph network for the estimation of confounders and dynamic prediction. The reconstruction is better than in the two previous baselines, but remains very approximate. Finally, our model manages to predict the entire counterfactual video with satisfactory accuracy, outperforming the baseline. Nevertheless, the edges of the object still appear a bit blurry. This is clearly a direction of improvement of our model. We also evaluated the model on a real-world version of Block Tower by Lehrer and co-authors. As this dataset only contains a few examples, we leverage the model trained on simulation and fine-tune the weights of the network on the new dataset. Our model still outperforms the baselines. Thank you for your attention, and I hope you enjoyed this presentation. I wish you a good conference, and do not hesitate to ask your question at the end of this session or during the poster session.